Suppose we are growing bacteria in a petri dish, and we want to model the number of bacteria as a function of time. So I can represent the population or the number of bacteria with the letter P, and T can represent time. And let's suppose that the rate of growth of the population of bacteria is proportional to the size of the population. Well, the rate of growth of the population, that's represented by dp dt, a derivative of the population with respect to time. And so our model here looks like dp dt equals k times p, where k is a constant of proportionality. That's the model that we're going to use. Okay, so here is dp dt equals k times p, and this is an example of something called a differential equation. We have a function p, and we have a derivative of that function, dp dt. And in general, a differential equation is an equation that contains an unknown function and one or more derivatives of that function. So let's look at a qualitative analysis and see if we can try and understand how to solve this equation. So here's the differential equation, dp dt equals k times p, and we're going to assume two things. We're going to assume that k, that constant k, is positive, and we're going to also assume that the population is positive for all times t, because it doesn't really make sense to talk about having a negative number of bacteria. If we assume these two things, then we also notice that dp dt is greater than 0 for all times t, because if you think about it, if k is positive and p is positive, then k times p certainly is positive, which means dp dt must also be positive. So the population is always increasing. And furthermore, as p increases, dp dt increases. So not only is dp dt positive, but it's also increasing. So if we look at what we know that the population p is always increasing. We know that the rate of growth of the population, dp dt, is also always increasing. And if you look at the equation here, the differential equation, the derivative of p has to be a multiple of itself. Well, what kind of function has these properties here, where we have a derivative and we get a multiple back of itself? And if you think about it, an exponential function seems to make sense here. So let's try letting p of t equaling c, a constant c, times e to the k times t power. Now later on we'll look at how to actually derive the solution to this differential equation, but for now let's just use this trial function here because it seems to make sense. So let's check it out. dp dt is the derivative with respect to time of c e to the kt, and this constant c can just be pulled outside the derivative. It doesn't depend on time. And then when we do the derivative of the exponential, we bring down a k, and I can bring the k out front, and I have k times c e to the kt. Well, c e to the kt is just p. So this says that the derivative dp dt equals k times p, and that was what we had up here for the differential equation. So yes, this does seem to make sense. It works. Okay, so here is the differential equation. And here's the solution that we discovered. And if we look at time t equals 0, that's plugging in 0 for t, we see that p at time 0 equals c e to the k times 0. But e to the 0 power, anything to the 0 power, is 1. And so this is just c. So we can think of c as the initial population. And we'll call that p with a little sub 0. So we're going to now write the solution as p of t equals p sub 0 e to the kt. So let's choose some specific values here. Suppose we have an initial population of 2 and we have a growth rate of 4%. And I'm going to rewrite that as 0.04. So then we have the function p of t equals 2 e to the 0.04 t power. And if I graph this, I get what you would expect, something that looks like an exponential function, something that starts off at 2 and then grows exponentially over time. So dp dt equals k times p was the model that we were using, but this model is a bit unrealistic. It doesn't account for limited resources, for example. Like in our petri dish here, the petri dish only has so much space. Eventually the bacteria are going to take up all the space and there won't be any more room for new bacteria. So we need to modify the model a little bit. And that's what we're going to look at in the next video.